Okay, so good morning, everybody. So let's get started. Uh, can you see my screen?
Yes, I can see.
Okay, thank you. Everybody, so as you know that last class we were discussing about the speed control of induction motor and then we were ran out of time. Today I will be continuing and then we will start the new chapter which is the synchronous machine. Uh, and then still I am grading your homework 1 and homework 2 and then for sure next class I will discuss about the solution and also before then either by tonight or definitely by tomorrow you can see your graded homework on eCourseware. And then I think next week September 22 coming Tuesday you will take your first midterm exam. So in next class I will be discussing about the syllabus, question pattern, exam duration, etc. in next class. So therefore, everybody please be present in next class. And that will be very important class for you. Okay, so as you can see, we were discussing these 5 methods that frequency change, pole change, input voltage control, and then rotor resistance control. Although that is only for the on rotor type only and then power electronic or solid state switching based control. And then someone you asked the question which one is the most important or most sophisticated. Then I said definitely the number D, power electronics based control. So in fact, like number DE, I mean both number fourth and fifth, rotor resistance based control and power electronic, both are popular. So while the if you say the best method or the most sophisticated, that is definitely the power electronics one. So I will be discussing a little bit on those 2 methods and then we will solve in on numerical problem. Uh, so for the rotor resistance based control, so if you remember, I think 2 classes back, once I showed you this picture. So this is for the wound rotor type, not for the squirrel cage type. Because in squirrel cage rotor, you cannot change the speed. There is no provision to connect any external resistor. So therefore keep in mind when it is rotor resistance control, that is only for the wound rotor type. So this is the picture of that wound rotor type. In this case it is a delta configuration. So both stator and rotor are in delta connection. And then you see with the delta, the external resistors are connected. So therefore now if you vary these resistance, accordingly rotor current will be changed, rotor voltage change, rotor flux will be changed, and that will change the torque and finally the speed. So that's why it is called the rotor resistance based control. So therefore, as I explained before, so this part is rotating, but this resistor is static. You know, this is external resistor. This is actually not the part of the rotor circuit. This is external. So this is moving. So you see the slip ring is written at the terminal. Those slip rings are also moving, but the black portion, black part is called the brushes, carbon brushes. This means with the external resistors, the carbon brushes are static, and while those are moving, they are just touching. They are coming in contact with the brushes. Consequently, the impact of resistance is going into the rotor circuit. Therefore, now if you vary this one from low value to high value, accordingly, rotor circuit current will be changed because rotor circuit impedance are getting changed due to the change of this resistance. So that's why it is called rotor resistance method. So and then as a application, I told that because you are changing, you are controlling the speed, meaning that this is variable speed operation. The application is variable speed wind generator system. Frequently, this method is used. Now, coming back to that method, power electronic based control. So, this is your power input, main power line, and this is your motor. This is your motor. This is the stator of the motor. Now, from here, you want to send power here to the stator. In this case, the main goal is to provide the controlled input voltage. This means here you have voltage that is connected to the power line. Here the voltage is fixed, but you want to make some change in the with the help of this arrangement so that the voltage here changed. Because if you can change voltage here at the stator terminal, that will change the stator flux, stator current, and ultimately that will impact the torque and hence the speed. So that is the method. So therefore, goal of this method is to control the input voltage, change the input voltage with the help of power electronics component. Accordingly, it is called power electronic based control. So now this portion, you all know, this is the rectifier circuit. It could be diode based, it could be thyristor based. So typically diode based. So therefore, there are 6 diodes. This is 3-phase rectifier. So what we will do, when you will supply input voltage, then here you will get the DC. But that DC may not be fully flat DC, fully smooth DC. There can be some sort of ripple or oscillations on the output. That's why you need a capacitor. So therefore, you all know the function of capacitor. It will provide a smooth output. So therefore, without the capacitor, DC voltage here is fluctuating a little bit, or there are much more ripples. So the capacitor will eliminate those ripples and provide a smooth DC. And then you see your this is induction motor, stator. Clearly, this is the 3 line. So definitely, it is the AC voltage. It is not the DC voltage because there are 3 lines. So this means here you have the DC. Now you have to convert into AC. That's why you see this arrangement. It is called inverter circuit. Inverter means conversion from DC into AC. So therefore, this portion is called rectifier. Rectifier means conversion from AC into DC. And conversion from DC into AC is called inversion or inverter operation. So accordingly, here this is there are again the 6 elements. So that will invert into your desired AC with desired frequency. So now here inside there are 2 types of components, as you can see. These are called the thyristors, these components, thyristors. And there are, you see, inverse parallel diodes. It is called the anti-parallel diode. There are 6 diodes as well. So, and then this capacitor is called DC link capacitor. You will be remembering this term, DC link, because you see this side is AC, left side, again right side is getting AC. So in between, it is kind of making a balance between left side and right side. So that's why it is called the DC link capacitor. Typically, this is small rated in the microfarad range, or it can be millifarad range, not in the farad range. This is not the very big value. Its function just to reduce the ripple, eliminate the ripple, and maintain a balance between the right side component and left side component. And also, as you can guess from your DC circuit knowledge, because this portion is DC and it's a capacitor, definitely it can store energy by the equation half C V square. So because it is DC, so definitely it will store energy. And in fact, that stored energy will be released, will be sent to the stator motor terminal. So therefore, the main goal will be to control here. you have to control the firing angle or the triggering angle of these diodes, or if they are thyristors, then their firing angle. So therefore, the first question is that if you apply the AC voltage here, how much DC you will get here? That is the first question, and how you can control. And then the remaining portion is the inversion, just convert from DC into AC. So therefore, for this portion, for if I have written down the equation. So I think you all know this equation from your electronics circuit course, EC 321 course. It is conversion from AC voltage to DC voltage, rectifier operation. So this is the equation. So you see in the equation, this is VDC, amount of DC voltage, output DC voltage, and 3 Vm over pi. 3 that is for the three-phase system. That's why 3. Vm is called peak or amplitude of input AC line voltage. This means that, like here you are applying the voltage. So your voltage is sinusoidal. What is the peak of the line to line voltage? That is the meaning of that Vm. So keep in mind, this Vm is not the RMS value. This Vm is the, clearly I have written, peak or amplitude. I mean, soon in a few minutes, we will solve a problem, then you will get it. And then cosine alpha, this alpha is that firing or triggering angle of diode or thyristor device. So because there are 6 diodes, accordingly it is called 6 pulse bridge rectifier or 6 pulse rectifier. For each diode, there is some delay. There is some delay. Immediately they cannot work. So that is called the delay angle or the firing angle or triggering angle. So probably from electronics viewpoint, you all know that every power electronic component has some sort of time delay, which is called firing angle. Immediately they don't work because those are the solid state device. You must allow some sort of delay. So that is that angle alpha. So I have written that is the firing or triggering angle of diode or thyristor device. So therefore I believe you have noticed this equation. Sorry, had someone said anything? Okay, so therefore I believe like you have studied or you have seen this equation in the electronics course, in the rectifier circuit or the DC to DC conversion or DC to AC conversion. At that time you have noticed this one. So therefore, so everybody say, this means that Vm is related to the AC voltage. You see, peak or amplitude of input AC voltage. So we want to apply the AC voltage here, and that we want to control so that the controlled input goes to the stator of the induction motor. So how much DC you will get here? It depends on the firing angle. You see, it depends on the firing angle. So this means this Vm is coming from your line. What voltage is available at your home or in industry, wherever the motor is used. Now you will get the DC voltage depending on the value of the alpha. So now clearly you can see, because this is cosine alpha, so alpha can be 0 degree, alpha can be 90 degree. So therefore if it is 90, then cos 90 is 0. So therefore, I mean, you can make the voltage fully 0 at the DC. And then 0 degree means that is the maximum value of DC voltage. Therefore, depending on situation, how much how much speed you need to control here, it depends on the system and application. Accordingly, you have to generate voltage here, control, and accordingly it will appear here. So for example, if it is 5 degree, then on value. If it is 10 degree, then on value. So therefore, main thing is controlling that firing angle with the help of some sort of controller. That is the goal. So therefore, based on that, I have set up a numerical problem. So everybody read the problem. To control a three-phase induction motor, suppose the following system is available. For example, this is your system. I mean, again, the same picture. If the firing angle of the rectifier diode is 5 degrees, this rectifier diode is 5 degrees, and a 100 millifarad DC link capacitor restores a 20 kilojoule of energy. So then I am talking about this capacitor. It has 100 millifarad value and it is storing 20 kilojoule of energy. Then what should be the input RMS line voltage? So what should be the input voltage here and RMS value? That is the question. Everybody, could you follow me so far? So everybody, do you understand the question? So this is the control setup for the three-phase induction motor, and firing angle is mentioned 5 degrees and 100 millifarad DC link capacitor value, and I'm telling okay, it is storing 20 kilojoule of energy. So based on this information, what should be the input voltage? So now this means that we have to utilize this equation. You see, this from this equation you will be getting the input side information. Look, peak or amplitude of input AC line voltage, which is Vm. So therefore, if you know what is this on, and if you know what is the firing angle alpha, this is pi, just constant number, then you will be getting the Vm. So now the question is, what is that VDC? So here, so that is not mentioned, but capacitor value is given 100 millifarad and it storage capacity is given, which is 20 kilojoule. So based on that, first you have to find out what is the voltage here, DC link voltage here, or the output voltage here, and then use that equation and then get the Vm. And this is your peak, then convert into RMS. So then you are done. So therefore for you here, I think I have solved the problem. So everybody see this one. So that is my basic equation, conversion from AC into DC. So here alpha firing angle is 5 degree, which was mentioned, this one. Firing angle is 5 degrees. So that I am putting here. Now, I don't know the DC voltage, but I know this relationship. EC have CVD. What is the EC value? EC value is 20 kilojoule. That is the storage capacity of the capacitor, and its value is 100 millifarad. So exactly I am putting the have C 100, I converted into farad, 10 to the power minus 3, and VDC squared. And then from there, I am calculating VDC value. So I got VDC value 632.46 volt. And then once I get that one, just plug in into that equation. You see, this is VDC value 3 over pi cosine alpha 5 degree. And then from there, I am getting Vm. But you know, because Vm is that peak or the amplitude of the AC side line voltage. So to get the RMS, I have to divide by root 2. So my final answer is 470.20 volt. Everybody, could you follow me?
Yes.
Yeah. Okay, great. So therefore, this is not difficult problem. Just you need to, you all know this equation. This equation also, as I believe we have learned in the electronics course, EEC 321 course. Just you need to remember this one, then you are done. So just keep in mind that this is not the RMS. I mean, sometimes students make mistakes. They thought that this is the RMS. So therefore, we have to go one more step. We have to divide by root 2. This is the peak. So that's why keep this on the peak or amplitude. Okay, so then moving forward, this is one important characteristics which is called the induction machine's torque speed characteristic, showing braking, motor, and generator action. Uh, Everybody see here what I am showing. Here I am showing three things. This portion, everybody see the middle portion is the motor region. The first of all, the y-axis is the torque and x-axis is the slip as well as the speed, motor speed. Slip as well as the motor speed, x-axis. And then I am plotting three things. Middle portion is the motor, induction motor region. Right side is that generator, induction generator zone or region. And then leftmost side is called the braking region. Now, first, because we are right now studying the induction motor and induction motor control, so therefore first look this portion. You may be asked this question, okay, draw the torque speed characteristics of induction motor. Then just draw this middle portion. If you are asked to, okay, also you draw the generator, induction generator torque speed characteristic, then you also need to draw this portion. Now, everybody see here, as I said that this axis is slip or the rotor speed. So now look this equation. So you all know this is the slip equation, ns minus nr over ns. So ns was the synchronous speed and nr was actually the rotor speed. Now at this point, you see it is written 0. 0 means the speed is 0. Like you are applying voltage, you are applying current to the stator circuit, but still motor is not running. That is the meaning. So you applied stator voltage created rotating magnetic field. That rotating magnetic field caused the rotor voltage, hence rotor current, rotor flux, and then some torque developed, but still motor has not started running. That is the meaning. So I mean NR is 0 at that moment, but slip value is 1. That's why it is written slip value is 1, and this 0 means that motor speed is 0. So, but at that time, there is some torque, there is some starting torque, and which is needed. So this means that induction motor has some standstill still torque, but steady state torque, even though the rotor has not started rotating. Motor is ready to rotate, motor is ready to operate. That is the meaning. And then gradually see, it is gaining speed. Now see that from the 0 value, NR value is increasing. Look the slip equation, it is increasing. Your torque is also increasing. At some point it is going. And then look the equation, NR increasing. When it will be equal to NS, look, then it will be 0. It will be 0. This means the slip will be 0. So that's why I have written slip is 0. When it is ns, this means nr value is ns. But what is that meaning? Meaning that next time, even though you apply voltage to the stator circuit, but that cannot produce voltage on the rotor because there is no relative motion. Synchronous speed and rotor speed has been equal. That is the meaning. That's why the slip is 0. As you know that you must allow some slip. Whatever it is, generator mode and the motor mode, you must need some slip value. So that's why torque was increasing. At some point, this is called the maximum torque or the pull out torque. After that, it will like fall down. And at this point, when the both speed are the same, the 0. And then again, you see, for example, you added some means. I told, for example, wind generator system. With the shaft of the induction machine, you added a wind generator or you put some auxiliary means that is increasing the NR. So therefore, this means NR is getting greater than the NS. For example, then what is happening? Your slip value is getting negative. See, if NR is greater than NS, your slip will be negative. And then that is the meaning of the negative torque. So therefore it is going down, 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 and then again in this side there is maximum value, and then it is the response. So therefore in this zone, sleep value is fully negative in this zone. So that's why it is called the generator region. Like I think 2 classes back I mentioned the for motor operation sleep is positive, for generator operation sleep is negative. And so sleep negative means this rotor speed is much more higher than the synchronous speed. The mechanical side is dominating, shaft side is dominating. That motor will start working as a generator and it will provide power to the grid. That is the meaning. So therefore you want, and then there is this portion, it is called the braking region. Um, Sometimes some industry use on method, what they do, it is called actually the plugging. The braking, sometimes it is called the plugging. Plugging means your motor is running at steady state at a good speed and you want to stop the motor. Therefore, instead of stopping the switch or instead of or disconnecting the line, what is done? They interchange any of the two leads, any of the two lines. Just swipe any of the two lines. Then your phase sequence will be changed and motor will start rotating in the reverse direction. And so reverse direction means gradually it will lose its torque and then at some point it will be stopped. So that's why in this zone, you see, the meaning that the NR is not in the indicated direction, it is in the opposite direction. So if it is opposite direction, then there will be another minus here. So minus minus it will be plus. That's why you see the sleep is in this zone like increasing, increasing, increasing beyond 1, even it might be 2. That is the meaning. And then you see the minus ns. Minus ns means that is the NR value. So and then motor will be stopped. So this is called the braking region, or sometimes it is called the plugging or the reverse braking. So this means that the once again, like you want to stop a motor, instead of disconnecting the line, what you need to do, you just interchange any of the two lines. You connect a phase to B and then B to A or B to C. Just interchange any of the two leads. Then motor will start rotating reverse direction and ultimately it will slow down, slow down. That's why it is called the braking zone. And at that time the sleep value is positive and sleep value is much beyond the 1. So that's why your more concentration will be this on the motor operation, and then sometimes you will be asked about the generator operation. So just keep these two things in mind. Okay, so moving forward, um, today we will start the new chapter, which is the synchronous generator. This is the generator which is actually used in real power plant. So everybody keep in mind, it is the synchronous generator. Or sometimes it is simply called the alternator, just alternator. So by the alternator, you will be keeping in mind that is the synchronous generator. I mean, mainly this is used, but sometimes, I mean, this book or some other books, or sometimes in some journal article, you might get this keyword alternator, meaning that that is the AC generator and synchronous generator. Okay, so therefore we will be looking at synchronous generator operating principle, and then again, because this is generator, this is the main power source in our real life. So how much voltage it induced, what is the induced voltage equation, and the pole construction is very important in this case. And those are the physical poles. I am coming soon. It is called salient pole and then non-salient pole. Salient pole means the poles are visible. Non-salient means the invisible. Poles are not visible. Soon I am coming those points, and then the followed by numerical problems. So first of all, uh, what I have written, like for synchronous generator, uh, So here there is some similarity with induction machine that we have learned so far. You know that induction machine has stator and rotor. Similarly, here it has also the stator and rotor, but the main difference is that in case of induction machine, there were no physical magnetic poles. So I believe everybody understood. In case of induction machine, there were no physical poles. We needed to create poles with the application of the voltage. Once you applied the voltage, there was current flowing, and those current flowing caused the rotating magnetic field. So therefore, there are internal magnetic pole created. In this case, you don't need to apply any voltage or anything because this is generator. It will produce voltage, but there are physical magnetic poles. So what I have written, stator or armature is stationary, but rotor or field rotates. And then just look this on for DC generator, field is stationary, but armature rotates. I mean, soon I am taking you to that whiteboard and explaining. Just you see, it is the reverse. For synchronous generator, I have written stator or armature is stationary, but rotor slash field rotates. And here I have written opposite thing. Field is stationary, but armature rotates. Armature or stator rotates. So therefore, why this is this arrangement? Why it is opposite? I mean, soon I will explain. So therefore, let me take you to that whiteboard for a moment. So everybody see carefully, then I will get it. For example, this is body. So let me draw two picture. Okay. Okay. So this is DC and then this is AC. This means this is DC generator and then right side, this is AC generator. AC generator means that synchronous generator that we will be looking today. So now, okay. So clearly you see this is the coil and then definitely you need the prime mover or the shaft is connected. This is the shaft and definitely shaft is rotating. Shaft is rotating with the help of a turbine. This is turbine T. Now, whatever the source is, it can be nuclear turbine, it can be steam turbine, it can be hydraulic turbine, or whatever, or it is wind turbine, whatever it is. You assume that this is the turbine, there is some fuel, or coal-based turbine, gas-based turbine, whatever, and shaft is rotating. Consequently, this coil is rotating. So this means that this shaft is connected with this body. This body is called that stator. This body is called stator. So you have learned this thing in induction motor. Or sometimes this body is called also the armature. Let me write the here, armature. So this body, this circular body, sometimes is called armature and frequently it is called the stator, on which there is a coil. And then this is the case of DC generator. And then what you need? To produce voltage, you need, of course, the magnet. So therefore, for example, this is North Pole and then this is South Pole. So meaning that everybody see, I mean, to produce the voltage, you need two things. You need a magnetic field. You need a magnetic field and you need a coil. This is magnetic field. For example, this is North Pole, this is South Pole, and this is a coil. So now the rule of voltage production is that either you have to move this on. Now you might move this magnetic field around this coil. Then the voltage will be built up. on this across the coil, plus minus. Definitely voltage will build up. Or you can keep this fixed, you rotate this coil around it. Therefore, either you have to move this one across the coil, around the coil, or you have to move the coil around the magnet. Either way, you can produce voltage. Now, now you can argue that, hey, I will move both. I will move both this one and this one. So if you rotate or move both, voltage will build up, provided that there is relative motion between this field and the coil. Now, if you rotate this on and this on at the same speed, for example, it is 1000 rpm, this is also 1000 rpm, you are moving both at the same speed, there will be no voltage. But if you move, you are moving both, but there is relative motion, one has 1000 rpm, other has 900 rpm, for example, then there will be voltage built up. So therefore, everybody keep in mind that to produce voltage, the basic rule is that you must need a magnetic field, in other words, a magnet and a coil, and voltage will be produced if there is relative motion. So now you can create relative motion either way, like either you keep this one fixed, you rotate this one, or you keep the coil fixed, you rotate this one, or you rotate both but maintain a relative motion. So now based on that, come back here. In case of DC generator, typically this body, stator body, on which the coils are placed, this coil means this coil, coils are placed, that coils is rotated with the help of the turbine. Now, like for example, this is rotating at 900 rpm, just an example. And then you see, I have placed North Pole and South Pole to indicate this one. You must need magnetic field. So therefore, the voltage will be built up here, and that is the DC voltage. And in case of the DC generator, it is hardly like 1000 volt. In most cases, it is much more low. It is much more low. The maximum voltage could be 1000 volt. Much more voltage is not produced in that way. Now, if it is AC generator, I mean the synchronous generator that we want to learn today, of course, because it is AC and it is three-phase system, there is A phase, B phase, C phase, not just only one set of coil. There are three sets of coil that you understand easily. And then definitely what you need here, you must need again the magnet. Again, you need a magnet here. Now, for example, the same way I am placing the magnet here, North Pole, and then here the South Pole. And then, for example, I need again the shaft because I have to rotate it. And for example, this is the turbine, whatever it is, coal-based, oil-based, nuclear-based, steam turbine, hydraulic turbine, wind turbine, whatever it is, you need a prime mover or the turbine. And for example, this is rotating. Now, everybody say that again, I made the similar arrangement. Instead of just one coil, I put three coils here. And I have the magnet because I need it. That I understood here. So now everybody look that I am rotating this one. So I am rotating this one means all three phases are rotating. A phase, B phase, C phase. And if you remember that at the very first class, I was telling you, typically AC generator produce 11 kV at the minimum. The range varies from 11 kV up to 13.8 kV. You can see it's a very high voltage. It is in the kV. But what I said here, it is maximum 1 kV in case of DC generator. So it is 1000 volt maximum. But in this case, minimum is 11,000 volt. Now, why I am emphasizing this number? Now everybody say, I am moving this on. Consequently, these three-phase coils are moving. And see, they are producing 11,000 volt. Now they are producing 11,000 volt, that is fine. they can produce voltage and they can send power in this direction. And but there is some precaution, there is some issue with this arrangement, or if you move the coils, uh, clearly you can understand, because this is F phase, B phase, C phase. It is not the way I have placed. Of course, there are some insulation, like there is insulation between A phase, B phase. Similarly, B phase and C phase properly insulated, and then accordingly C phase and A phase properly insulated. Why there is insulation? So that there is no short circuit happens between A phase, B phase, and B phase, C phase, or C phase, A phase. In case of DC, it is only one set of coil. I mean, there are many number of turns. It is not just only was a simple coil. There are many turns, huge turn, but at least one set of coil, that you understand. But here there are three different coils, A phase, B phase, C phase, because this is three-phase system. That's why each phase are properly insulated. I mean, there is proper insulation between any of the two phases so that they don't make any short circuit. Now, why I am emphasizing this insulation, now everybody come back. I am moving this on. With the help of the shaft, these three sets coil are moving. And then typically the movement can be 3600 RPM, or like even 1800 RPM, it could be have, but still it is too much RPM. At that speed it is rotating. And if it rotates at this speed, what is your guess? Because it is producing 11 kV very high voltage. And then, I mean, next question is how you will take the power from here, because you see that these things are moving. You can argue that, okay, I can take power with the help of slip rings and brushes. That is also true. There is no problem. But the problem is that because this body will rotate, during rotation or after a long term rotation, maybe not immediately, maybe 1 year later, 2 year later, this insulation might be lost. The insulation might be broken. And also because this body is moving, there is centrifugal force. I mean, from the physics, there are two forces, centripetal and centrifugal. So centrifugal means force outward. So therefore, these coils, F phase, B phase, C phase, these coils may be deformed or may be displaced, because continuously, year after year, month after month, they are moving. So you understand? So those things. That's why in case of the AC generator, the common practice all over the world, these coils are not rotated. These coils are kept fixed. So therefore, what is rotated? You have to rotate the magnetic field. So that's why magnetic fields are not placed here. In case of the AC generator, they are placed here. There is another body. Sorry, there is another body. This body is called the rotor body, and you place the north pole and south pole on that rotor body. Therefore, now because you see the north pole, south pole, this body, which is the rotor body, that is connected to the shaft. So when whatever speed it is rotating, this means only the north pole, south pole is rotating. Your coils are fixed. So now you are safe. Now whatever voltage you can produce, 11 kV or 13.8 kV, or it could be up to 20 kV, because the coils are not moving. So you can guess that the insulation will not be damaged, insulation will not be deformed, coils will not be displaced or the deformed over the time. Of course, there can be some dust or impurities at it over the time. So you need maintenance. That is different thing. But at least there is no issue because they are not moving. That's why, I mean, what I am emphasizing side by side, in case of AC generator, everybody keep in mind that this body is called that stator. This body you all know. So stator remain fixed, and this body is called that rotor. This body is called the rotor. Rotor moves with the help of the shaft and turbine. This means magnetic field will be placed on the rotor body, that will rotate. In case of DC generator, because it is only one set of coil and they will produce less voltage, it could be maximum 1 kV. That's why typically this body is rotated and then the field remains static. I mean, you could do the opposite thing as well. Of course, voltage will build up, but all over the world, common practice is to rotate this body and fix the magnetic field. So therefore, if you are asked this question, what is the basic difference between DC generator, AC generator? So therefore, don't say that okay, AC generator produce AC voltage, DC generator produce DC voltage. I mean, as an engineer, don't say that on at first. That, I mean, you may say, of course, that is true, but don't emphasize that point. As an engineer, you will be answering that in case of AC generator, the armature or the stator remains static and the rotor rotates or the magnetic field rotates. Here you will be telling in case of DC generator, coils rotates or because the coils are placed on stator. So stator or armature or the coil rotates with the help of shaft and turbine, but magnetic field remains stationary. So that will be the first engineering point. And then you can say that DC generator produce DC, AC generator produce AC. But don't say that one as the first point. Everybody, could you follow me what I said so far?
Yeah, definitely.
Yes,
Yes,
yes.
sir.
This is very, very interesting and very important. So now everybody come back there. I'm taking you there. So see, those are the things I have written. Now everybody see. For synchronous generator means that is the AC generator actually. You see, stator or armature is stationary, but rotor slash field rotates. Just to explain. For DC generator, field is stationary, but armature or stator rotates. So you will be mentioning this point first, and then you will be telling that synchronous generator produces three-phase AC, DC generator produces DC. And then I will be asking you why this one? Why for synchronous generator, stator remains stationary and field rotates? Then you see, already I discussed, you will be answering these things. For synchronous generator, armature is kept stationary due to the following reasons. High voltage 11 kV, 13.8 kV usually is produced in armature or stator coils. If armature rotates, then during movement, insulations among phase coils might be broken and short circuit might occur. Also, during movement at a high speed, the stator coils might be displaced or deformed due to centrifugal force. This is the thing exactly I asked. Is everybody fine?
Yes.
Okay, great. So now everybody concentrate this thing, then we will discuss much more that rotor or field rotates. So field, so therefore in case of synchronous generator, because field is rotating, so that is of utmost importance. That is of high importance. So there is further or subsequent discussion on that. Now everybody see that pole, that magnetic field is two types. One is called salient pole machine, other is called non-salient or cylindrical or round rotor machine. Now that magnetic pole, how does it? So first look this picture. Okay, this is the picture for salient pole rotor. So can you see these are actually that magnetic poles, North Pole, South Pole, North Pole, South Pole. There are many poles. This is the realistic picture. So therefore, you see, this is the shaft because rotor circuit, and on the shaft the magnetic poles are placed. This means with the turbine, when this thing will move, automatically the magnet will move. And in this picture, everybody see non-salient pole rotor. Can you see where is the pole? Is it visible likewise this thing? Can you see here? So I mean, inside there are poles. Those are inside, yeah, inside, yeah. But those are not visible from outside. accordingly it is called non-salient. So the meaning of the non-salient is non-visible, invisible. That is the meaning. So you all know the salient means the main, or the chief characteristics are the main. That is one meaning salient. But in this case, for electrical engineering term, non-salient means invisible pole, because from looking outside, you cannot see the pole. There are pole, but inside. And in this case, the poles are on the outside of the circular body, outer rim or outer surface. In this case, these poles are inside. And in this case, you see, there are many, like 1, 2, 3, 4, 5, 6. It could be 20, it could be 40 poles. In this case, typically very less, maybe 2, sometimes only 2, sometimes 4, hardly it is 6. Typically, common practice is 2 to 4 in this case. And only 2 to 4, that's why in this case you need less space, and its diameter is less. But in this case, you can guess, because you have to place many poles, so its circumference and its diameter is larger than this one. Now the question is, what is the motivation to use this one or this one? Why those poles are placed on the outer surface using a larger diameter or larger circumference, versus why in this case the poles are invisible and only less numbers of poles are used? That is an important question. What is the reason? Or as an engineer, when to choose this one, when to choose this one? What will be your basis? What will be your rationale behind choosing this versus this one? So that's why everybody say, come back to that equation. Let me once again take you to that whiteboard. It will help you. Okay. So we were discussing those things. So let me draw those two pictures. Like you noticed that poles are placed in that way. Poles are placed in that fashion. And then this is your shaft. And then this structure is your salient pole type. This structure is your salient pole type. And then let me draw another one, and then we can discuss. For example, just say this one. In this case, this is North Pole, South Pole. I just drew only 2. In this case, there are many. For example, North, South, North, South, North, South. Even there can be much more. So, and then this structure is non-salient type pole. Now, everybody say that your turbine will be connected here. This is your turbine, okay? And that turbine, if the input is, it can be coal. If the coal is available, it can be gas, it can be oil, it could be nuclear, or it could be steam turbine. You see, accordingly, probably you might have noticed the nuclear power plant, gas power plant, coal power plant, steam turbine power plant. Accordingly, the power plant name goes according to the input availability, or it can be hydraulic. It can be hydraulic. It can be hydraulic. I mean, the hydroelectric power project, if the input is water, like water falls on the turbine blades and then it moves. So that whatever the input is, this is moving. Okay, so in this case also, input could be any of those and then it is moving. Now, I am discussing what is the difference, but I am trying to make you understand when to choose this one, when to choose this one. Now everybody come back this equation. What is the synchronous speed equation that we learned in case of induction machine? Same equation applies here, 120F over phi. This is the equation in RPM. So this will be the speed of this shaft or this shaft in both configuration. Now everybody say, what is the frequency of United States? It is 60 Hertz. This number is fixed. This means whatever the generator, whatever the pole you choose, this type or this type, your frequency should be fixed. That is 60 Hertz. As a customer, you want that one. Now here you see this thing. Now if everybody look the equation, if the pole number is 2 and this is 120, this is 60, then you will be getting 3600 RPM. And then everybody look, if this number is 4, pole number is 4, then you will be getting half. You will be getting 1800, right? Everybody say, I am not changing the frequency. Frequency is fixed because I want this frequency. So only two things I am changing. When I am changing the pole number, then my speed is changing, it is reducing. Or again, so you can make like half of that, 900 for example. You can reduce. Now, why I am reducing these things? Now, everybody keep in mind, typically if it is coal, gas, oil, nuclear and steam turbine, these are the fuel input. They produce, by natural, they produced very high speed on the turbine, around this range, 3600 RPM. But when it is hydraulic turbine, you know that because it depends on the waterfall, water falls on that turbine and then that produces torque or the rotation. Typically its speed is low. So in case of hydraulic turbine, typically it is like 900 RPM. Naturally that is low. Hydraulic is not like coal, oil, gas or nuclear or steam turbine. Naturally low. Now everybody see, for example, you want to install a hydraulic turbine here. So hydraulic turbine, so therefore what is your speed going here? What will be your speed? You have to choose 900 here because that is coming from your system, natural system. It is 900. So if it is 900 here, everybody say, if you want to maintain 900 here and you want to maintain 60 Hertz here, so what should be your pole number? Pole number definitely should be much higher, not 2, not 4, much higher, right? Probably 6 or 8. On the other hand, everybody say, you want to use a coal, gas, oil, nuclear, any of these turbine. Naturally, they will provide you very high speed at this range, 3600. Now look this equation. If 3600 goes into this equation and you want to keep frequency 60 Hz, definitely your pole number is getting only 2, maximum 2. I mean, see the equation. NS is 120 F over P. You want to keep frequency 60 Hz. So therefore, when it is high speed 3600, you cannot use more than 2 pole, meaning that only on North Pole and then South Pole. That is enough because you cannot change this factor. So you cannot make any adjustment here. You want this on as a customer. If you get higher frequency, lower frequency, then your connected device, your loads will be damaged. There is negative impact. So now the thing is that I am explaining this versus this. So in salient pole type, you see, because the poles are placed on the outer surface of this body, you can place many poles. I mean, typically 20. And then I mean, it starts from the 6, 8, and goes to 20. In this case, it goes like typically 2 to 4, very frequently 2 to 4 for this type. So that thing I am explaining, when to choose many poles machine, when to choose less poles machine. It depends on your what input you are using. If you are using coal, gas, oil, because they produce naturally the high, RPM, high speed, you have to choose this one. And if you choose hydraulic, then you choose this one because you can increase the pole number here. Accordingly, your speed value will be reduced. You will get less speed here by using this equation because you want to keep frequency 60 hertz. Now come back this point. Everybody, like you answer me, at University of Memphis, can you install a hydraulic generator system? Can you? So just answer anybody. So can you install a hydraulic system at University of Memphis campus? The answer is no. Why? Because hydraulic system, how you will get water? You need a lake, you need a river, you need a waterfall. So how you will create that? I mean, you can argue, okay, I will dig, I will create hole, I will dig the land or the soil, I can. But definitely you need a huge space, probably the whole area of University of Memphis. So nobody will allow you, not the university, government will not allow you. So therefore, to place the hydraulic turbine, you have to go nearby the lake or the river or nearby the ocean where there is water available. It does not depend on your choice. Similarly, can you put a gas turbine or coal turbine at University of Memphis? Again, the answer is no. Because the coal gas might not be available, you don't know the geography, whether there is natural source of coal or gas at University of Memphis or no, at not. You don't know that yet. So therefore, the location where coal and gas are available, accordingly, you have to choose coal turbine or the gas turbine or oil turbine. So do you understand what I am telling? So therefore, it is not your choice. It depends on the geographic location of the world, whether you have to place the hydraulic turbine or coal or gas, oil or nuclear based turbine. It depends on the geography. That geography will determine whether to choose this type or this type. So therefore, typically because this provides, any of these provides the higher speed, at that time you have to choose non-salient pole so that you can design with less number of poles because you have to maintain frequency. Look this equation, because you must maintain frequency 60 hertz, whether this type or this type. When you have the much less speed, like hydraulic case, then you choose salient pole type. So therefore now everybody go back there, that slide. So this versus this. So just keep in mind, in this case, there are main feature, there are many poles. In this case, there are less poles. Now come back to that slide. What I have written, salient pole machine, poles are visible, many poles. Diameter is big, axial length is small, exhibits low speed. Because there are many poles, by using that equation, you are getting, they provide low speed. And what is the example? Hydroelectric generator that just now I explained, or diesel driven generator. Typically, if it is diesel driven, they provide very low speed. So you have to choose salient pole machine. And in case of non-salient pole, sometimes it is called cylindrical rotor type or round rotor type of machine. These keywords are also available in literature or in the book. Poles are invisible, only 2 to 4 poles. Diameter is small. Axial length is big. Exhibits high speed. Example, turbo generators. This means turbine driven generators. And then I have written that point. It is the geography that determines the type of the rotor, whether it is salient pole or non-salient pole. You have to go based on the geography. geographic location of the world. If it is water available, then choose this one, hydraulics. If the diesel is available, then choose this one. And then because you can use manifolds, so you have to choose this one. If it is gas, coal, oil, nuclear, those are steam, those are available, use this one, turbine driven generator. Then you can use less number of poles. Consequently, you can maintain that 60 hertz frequency. So everybody, could you follow me what I am emphasizing and explaining?
Yep, sure can.
Great. Yeah. So therefore, if you have any chance to, I mean, now the coronavirus pandemic is going on, we cannot visit any power plant, definitely. But later, if you get any chance, even through IEEE, any visit, if you visit any power plant, then definitely you can see either they are using non-salient pole and salient pole. So definitely you all will be asking them one question, that what type of pole are you using, this type or this type? So then they will answer, and then really you can see those poles. Really those things you can see, I mean, by your eye, including the shaft system and the whole generator. Okay, so then moving forward, okay, we understand that whether it is salient pole, non-salient pole, and then coils are producing voltage. Now, what is the amount of that induced voltage? So now you see, I have written that induced RMS voltage equation of any phase of the three-phase stator. This is for any phase. EF 4.445 FN kW. Is that I was showing exactly the same equation in case of induction machine also. So the same thing. So here the phi is that flux per pole, F is the stator frequency, N is the number of turns, and Kw is that stator winding factor. And this is the equation for any phase. And this is the RMS value. Keep in mind, this is the RMS value. So now everybody write down this equation in your note, and then now I will discuss on numerical problem, and then we will be done for today. Everybody read this problem. An elementary two-pole, three-phase, 50 hertz alternator. You see the word alternator means this is synchronous generator. Has a rotating flux of 0.0516 Weber. The number of turns in its phase coil is 20. Its shaft speed is 3000 revolution per minute, and its stator winding factor is 0.96. Based on that, determine the following: the angular speed of the rotor, V, the three-phase voltage as a function of time, C, the RMS line voltage of this generator if the stator windings are connected in delta, and D, the RMS line voltage if the stator windings are connected in Y. So, I mean, the four question. So therefore, once again, everybody see, this is a three-phase generator. Flux is given, number of turns are given, speed is given, and stator winding factor is also given. Now find out this thing. So I have written down the answers here, and then in the next slide, I have solved that one for you. So the first of all, the angular speed. In fact, the speed was given. You see the third line. Its shaft speed is 3000 revolution per minute. So the first question is easy. You just convert into radian per second. That is the angular speed. Convert into omega. That is the meaning. So 3000 then multiplied by 2 pi over 60. That is your radian per second. So after calculation, you are getting 314.16 radian per second. Now, the second part was we find out the three-phase voltages as a function of time. Now, three-phase voltage, this means find out VA, VB, VB, VC, and express them in terms of time function, time domain function. That is the meaning. So just now we looked at this equation. You see this one. This equation is for any phase. For example, for phase A, and that is the induced RMS voltage equation. So Here I am using that equation, EA 4.445 NKW. I am plugging all numbers. Everything is given. Yes, here. This is flux value, 20 is number of turns, and this is the winding factor, 0.96. And the frequency is 50 Hertz in this case. So I am plugging all those numbers and I got approximately 220 volt. Now that is the RMS voltage. Everybody keep in mind clearly it is the RMS voltage. Now the question was find out the three-phase voltage as a function of time. This means you have to write in terms of like VA, VM sine of omega t in that format. So therefore, when you want to express in time domain, definitely you need here the peak or the amplitude. So that's why everybody say what I am doing. This 220 I got for phase A, I am multiplying by root 2 to make it amplitude or the peak value. And then sine of omega t. This is my omega, that angular speed, 314.16. So then after multiplying root 2, it is giving 311.13 sine of omega t. And then just write down the expression for B phase and C phase. What is B phase? 311.13 sine of this one minus 120 degree and C phase plus 120. So therefore these two are really just this one. Everybody, could you follow me what I am doing?
Yeah. Yes.
Yeah, great. Yeah, yeah. So therefore, only thing you remember this equation and just keep in mind this is the RMS equation and this is for any of the phases. And then because to express VA, VBBC, you need the VM, which is the amplitude or magnitude. That's why I just convert the RMS value into the magnitude from the AC circuit knowledge that you have learned. Okay, so then moving forward, there are two more questions. Question number C, everybody see. What is the RMS line voltage of this generator if the stator windings are connected in delta? Now you see, because this is three-phase system, stator windings could be connected in delta or Y. I mean, always we are discussing in case of previous chapter, induction machine, also the same thing. And then very first chapter, always, if it is three-phase system, it could be delta or it could be Y. So the question number C and D, that what is the RMS line voltage if stator windings would be connected in delta? And then the same question, what would be the line voltage if the stator windings would be connected in Y? So therefore, everybody see, if the stator windings are connected in delta, then what happens? In case of delta, phase voltage equals to line voltage. Voltage will not be changed. That's why question number C, you see, RMS line voltage 220 volt. 220 volt. You see, this is the phase voltage for phase only. But because question number C was for if the stator windings connected in delta, for delta line voltage, phase voltage same. So I just straightforward wrote down this answer without doing anything because this is delta. Now question number D, the RMS if the stator windings are connected in Y. So here I have to change. What's the relationship? Line voltage equals to root 3 times of the phase voltage. Line voltage equal to root 3 times of the phase voltage. That's why it's a 220, meaning that this phase, and then I'm multiplying by root 3. So I got 318.05 volt. So everybody, could you follow me?
Yep.
Yes. Yeah. I mean, this is pretty easy. So therefore, I mean, similarly, there will be other problems in this chapter, those we will be looking. Now, I will go a little bit more and then I will stop today. Here I have written one thing, excitation system. Now, everybody see, couple of minutes ago, we discussed salient pole and non-salient pole. This means there are physical magnetic poles. And what is the function of those poles? They will provide you the flux. They will originate flux. Otherwise, there will not be any voltage. Now, the question is, how does a magnet originates flux? This means a magnet should have proper magnetization. It should be magnetized. So that's why there is one system, it is called the excitation. Excitation means you have to excite the magnet. You have to create magnetism inside those physical magnet. This means how to excite, how to magnetize. You have to connect some DC source. You have to connect some DC. That is the main thing. So this means that then once again, like for a moment, let me take you there. Let me delete these things. Okay, so therefore, like you have a, for example, you have a magnet and it has north pole, south pole. It is not like that easily it will provide you the flux. So therefore, you need some sort of winding. Like for example, you have to place some coils or winding, and then this is the DC. This is that like VDC, for example. You have to send some power, DC power. So meaning that if this is DC voltage, then DC current is going, and that DC current, that DC current basically will excite this magnet. Consequently, they will originate flux. And then this is, if this is north side, this is south side. So you all know from physics, flux will originate from north pole and terminate in the south pole, or like this way. So therefore this way, it will start from north pole and it will terminate in the south pole. And then inside the magnetic material, it will flow from south pole to north pole. That is the typical direction of the flux that you have learned even from the physics long ago. So therefore, to create this situation, to create this flux or the field, you have to excite this magnet. That process is called that excitation. This process is called the excitation system. This means with the application of DC voltage, you have to magnetize. You have to excite the magnet, physical poles. That process is called the excitation. And this is very, very important. I mean, soon in probably next class or other class, we will be looking, depending on how much DC, how much current you apply, power factor can be leading, lagging, unity power factor. This excitation has huge role on the power factor control. It can be lagging power factor, it can be leading, it can be unity power factor. Pretty interesting. So that's why we are looking the excitation system. So therefore now, given this one, then once again go back there and then I will release you for today. You see, excitation system. So everybody see, I have written down for you. The basic function of an excitation system is to provide direct current, meaning that the DC, to the synchronous machine field winding. Just now I explained. In addition, the excitation system performs control and protective functions essential to the satisfactory performance of the power system by controlling the field voltage and thereby the field current. Now, depending on that excitation system, it could be DC excitation, it could be AC excitation, and it called the static excitation. Now, DC excitation, clearly you can understand that the providing the DC. AC excitation, although it is AC excitation, but ultimate goal is to provide the DC voltage. So everybody keep in mind, in a magnetic field of electrical generator, always DC is applied because DC can provide the non-fluctuating flux. They don't vary with time. That's why for a smooth and steady operation, you need the DC flux. So AC excitation means, this does not mean that you are applying directly the AC to the magnet. AC excitation means you have a small AC generator, and from that generator, with the help of rectifier, you are converting into DC, and that DC is going to the field. Just simply keep in mind the very first line. The basic function of the exciter is to provide direct current. It is always direct current, but there are three arrangements. There are three systems to provide that direct current. That is the meaning of this one. So therefore, DC excitation means really you have a DC generator mounted on the rotor circuit. AC excitation means you have a small, very small AC generator that is converting DC with the help of rectifier, which is finally being given to the field circuit. Static excitation means you don't have any DC generator, you don't have any small AC generator. You are taking the output from the stator terminal, and that thing you are, after converting into DC with the help of a rectifier, you are giving to the field circuit. That is the meaning. So therefore, just for a minute, again I will take you so that you can understand that one. Okay, let me erase this one. So therefore, once again, this is your like stator. This is your stator, like A phase, B phase, C phase, and then inside there will be rotor. This is your rotor circuit. So here you have that North Pole and South Pole. So we were discussing that three things here. DC excitation, and then AC excitation, and then also we are telling that static excitation. Three types. So therefore, DC excitation, so everybody see, because this is the rotor, so the magnetic field will be rotating with the help of the turbine and prime mover, whatever. So DC excitation means, of course, you will be providing the DC on the magnetic coils. So therefore, there are coils here, North Pole, South Pole. And then DC excitation means you have a small DC generator here. That is also on the rotor circuit. Everybody keep in mind, this is the rotor circuit, this circular body. So therefore, on the rotor body, there is North Pole, South Pole, physical poles. Simultaneously, at the same time, there is a small DC generator. So therefore, because this body is moving, so therefore this DC is connected on end here, other terminal is connected here. So in that way, the whole thing is moving. That is the meaning of DC excitation. AC excitation means instead of a DC, you have a small size of AC generator here. And then because you have to provide DC on the coils, you can easily guess, definitely there is a rectifier with this small AC generator. So meaning that when this shaft is moving, the whole arrangement is moving. This magnetic field is moving, that small AC generator is also moving together, which is rectifier. That is called AC excitation. Static excitation means there is other type of arrangement. Neither you have a DC generator here, nor you have a AC generator here. The concept is take the output of these three into a rectifier circuit. Here you have a rectifier circuit. This is rectifier. that rectifier is producing DC. This is your DC. And then you provide that DC into those two coils. So now the thing that here the challenge is that because this thing is moving and then you are giving this portion is static, but you are giving the voltage there. That's why you need slip ring here and you need the carbon brass. You need the carbon brass here. These are the brass. The brasses are fixed and slip rings that is moving and that is touching this brass. Consequently, you are able to provide the DC. But because this system is connected to the directly the armature or the stator output terminal, and these terminal are statics, accordingly it is called static excitation. Now it depends on, I mean, all over the world, some country use this system, some country use DC excitation, some countries use AC excitation. It just depends on the choice, how the originally the generator was built. But all three systems are prevailing all over the world. So that's why I'm bringing into your attention. So therefore, there's simply DC and AC excitation means there is a small DC or AC generator mounted on the same shaft, mounted on the same rotor. Static excitation means, as the name goes, static. Output is being taken from static three-phase terminals and then taken into rectifier. Rectifier is converting DC with the help of slip ring and brushes. That DC is being provided to the magnetic coils. So everybody, could you follow me what I said?
Yes, sir.
Okay, great. So with that, I think now it is 11:08. So I like to stop here.